Next type of graphs, we're going to look at absolute value graphs. Now we saw the basic absolute value graph, but we're going to, well, I'll be honest with you, I might get a bit carried away here. But here we go. So if y equals the absolute value of function x, that's the one we've already talked about where the bit below gets reflected above. Basically, well, it's not actually symmetry. When you look at it, it's not symmetric. But what I'm getting at with symmetry in the x-axis there is the bit that's below reflects above. So that little bit sort of becomes symmetric. It goes from below above. There's random graph. So if I had to do absolute value function x, what we're saying is we can't end up with a negative answer. So all these negatives will become positive. So it has the effect of flipping it up. So that goes and flips up. So that would be the absolute value of function x. But anything below, we just flip it above. Whereas function absolute value x is the other way. It's now the y-axis. Now this one will appear symmetric. Okay? So whichever bit is positive will get flipped over. So on this one, we can substitute in negatives, but we can only get the answers for the positive x values. What that basically means is anything to the left of the y-axis disappears, because we can't get those answers. And then what's over on the right-hand side reflects over, because this is function absolute value x. So you're subbing the x value in first into the absolute value of x. So when you substitute in, say, negative, well, let's say that's negative 1. When we substitute in negative 1, before we can put it into the function, it becomes positive 1. So you get the same answer as positive 1. When you substitute in negative 2, it's absolute value of negative 2. So you get the same answer as 2. So that's why you get a reflection that way. Function absolute value of x, it's basically the x values that are affected, whereas the one we did before, when it was absolute value of the whole function, it's the y values that got affected, so that the below got reflected above. Absolute value of y is equal to function x. So the absolute value of y is equal to function x. This one does have symmetry in the x-axis. This is a bit like the function absolute value x, where we're going to reflect the function x where it's positive. So easier to show you with a picture. So here's the random graph. The bit below, once again, has disappeared, but then the other one gets reflected over. Because this is absolute value of y is equal to function x. So function x, both plus or minus y. Because remember, absolute value of y could be plus or minus y. And so that's why you get the reflection this way. So that's absolute value of y is equal to function x. So I might be getting a bit carried away now. What about if you had absolute value of y equals function absolute value of x? Well, now we can build this from the two previous ones, because I could draw y equals function absolute value of x and then apply the absolute value of y to that. So you end up with symmetry in both the x and the y axis. There's a description what ends up happening. You end up with just the first quadrant gets put into all four quadrants. Let me show you why. Here's random graph. Everything else goes away. It's just the first quadrant, and then we just reflect that through to all the quadrants. Why? Well, because the first quadrant was where everything is positive. And so absolute value of y, function absolute value of x, everything is positive. So we just want what's the quadrant where everything is positive, and that goes into every quadrant. So you'd have something like that. Yeah, I kept going. What about y equals the absolute value of function absolute value of x? I could combine two of these other ones. I could do, which one would I do first? Function absolute value of x, and then do the first one and find the absolute value of that. So you end up with symmetry in the y-axis, but we also get reflection in the x-axis. There's a description of what we end up doing, but again, let's do it with a picture, it's easier. There's random graph. So first of all, I would draw function absolute value of x. And remember, it looked like that. But now I'm saying the absolute value of that, which was anything below, reflects above. And so we get that shape. No, I didn't stop. Okay, absolute value of y equals the absolute value of function x. So I could combine, which ones would we combine? We've got the first one and the third one. So I'm combining those. I'd end up with symmetry in the x-axis and also reflection in the x-axis. There's the description, here's the picture. Okay, I'll do absolute value of function x first, but then we're going to go absolute value of y, which said, oh, anything above reflects below. Whoa, look at that one. Absolute value of y is equal to absolute value of function x. Now, as I say, I've got pretty carried away with that, but you can get some wonderful graphs playing with absolute value. The reality is we're probably only going to see definitely the first one, absolute value of function x below, above. Function absolute value of x, definitely, could have that one. Maybe the third one. And after that is when I'm probably getting a bit carried away. But if they do, from that point on, it really is just a combination of those ones. It's a bit like a composite function, really. You do one and then apply the next one to it as well. Square root graphs. These are great. Again, we would first draw a graph and things to notice when you find the square root of a graph. Now, we know these things. You can only find the square root of a positive number. So anytime I have to find the square root of a function, I just get rid of anything below the axis because I can't find the square root of that. It would no longer be in the domain of my function. So I'll always end up with a positive number because we're saying what's the positive square root? So random graph, if I was to find the square root of this one, the first thing I'd do is go, well, anything below doesn't exist, so goodbye. That's the graph I'm working with. Stationary points will still be stationary points. That's not going to change, but their y value might change, of course, because you're finding the square root of those points. So on our one, I've got rid of the one that was down here. It's disappeared. The only one I've got now is up here. It's a number that's bigger than 1. Now, if you find the square root of a number bigger than 1, it gets smaller. So I'll plot it about there. I'll put it down a bit. It's still going to be bigger than 1, but it's certainly going to be smaller than where it originally was. Okay, now the asymptotes and the discontinuities. Once again, discontinuities going to remain. I mean, if it wasn't in the domain of the original function, can't be in the domain of the new function. The horizontal and oblique asymptotes, they're going to change. Again, work out what the square root of the asymptote is. In R1, I've got a horizontal asymptote that's less than 1. Find the square root of a number that's less than 1, it gets bigger. I mean, it won't go bigger than 1, but it will get bigger. So I'll put mine about there. I'll put it there. This is similar to the squared one that we looked at, but the other way around. If you find the square root of a number that's bigger than 1, then it gets smaller. So this time the new curve would be below the old curve, whereas if the original curve is less than 1, then the square root would go above the old curve. So a similar idea, but the other way around. That again means 1 is a very important number because the square root of 1 is 1. So I'll plot those 3 points. I know we're at those 3 points. Now the x-intercepts, this is where we've got to really look at these closely. What's happening at the x-intercepts in these graphs? So let me show you something. So y equals x to the power of some fraction a on b. The graphs become interesting and there is a pattern. So I'm doing where b is 3, so the cube root. There's y equals x to the power of third, what it would look like. That would be x to the power of 2/3. The 3/3 obviously is power of 1. So if the fraction is less than 1, so these two, they're less than 1, you've got 1/3 and 2/3, the curve will be concave down in the first quadrant. So you'll notice both of these concave down in the first quadrant. But the other thing about the x-intercepts with these group graphs is you get a vertical tangent. So you see how here's 1/3, there's a vertical tangent. If I was to draw a tangent to the curve, it would be vertical. Same with this one. This is what we call a cusp, but there's a vertical tangent. So you get sharp points like the cusp, or that inflecting shape like power of 1/3 that has an inflecting shape. It's going to do something like that. Well, now we're drawing square root graphs, so we shouldn't really see ones like the third because we won't go below. We might see cusp because that bounces back up and it gets positive again, but we will get a vertical tangent. Once we go bigger than 1, what happens. So there's 4/3, 5/3, 6/3, and I could have kept going. But now notice in the first quadrant the curve goes concave up rather than concave down. And we end up with a horizontal tangent rather than a vertical tangent. So when the power goes over 1, then we end up with horizontal tangents and concave up in the first quadrant. Here's a picture of several ones to illustrate that idea. See, if the original graph was x to the power of 4, well, if I find the square root of that, well, that's nice and easy because the square root of x to the 4 is x squared, so we know we're going to get the parabola. The interesting one is when you get to y squared equals function x. So rather than writing it as y equals the square root of function x, y squared equals function x has a different picture. Because remember, the solution to y squared equals function x is plus or minus the square root. And so you get a reflection like that. So x cubed, there's the original graph. If I find the square root of that, well, the power would become 3 on 2. That's bigger than 1. So I know it's concave up. And I have a horizontal tangent there. And it stops there because below you can't find the square root of the negative there. So it just stops like that. And if it was y squared equals function x, you get that cusp shape again, but this time it's sort of horizontally cusped rather than vertically. If the original one was x squared, well, square root of x squared is x, but it's also minus x as well. You get that similar to the absolute value shape. So you get a V happening at that point. And if it was y squared equals function x, you actually end up with a cross, because that now gets reflected below. If the original graph was 5/3, 5/3 would have a similar shape to a cubic, but the square root of 5/3, I'd end up with 5/6. And that's a number that's smaller than 1. So then I know, oh, well, that's concave down, and I get a vertical tangent. And if it was y squared equals function x, then you get what looks like, a parabola. It's not a parabola, but that U shape, but on its side. I guess you'd call it a C shape. 4/3, if you found the square root of 4/3, that would become 2/3. That's a number that's less than 1. But in this case, we get the cusp shape because the original graph, it's still positive over there and you can find the square root of a positive number. The one before it disappeared because you can't find the square root of the negative number, so it disappeared. But here it exists. So you get that cusp shape. And then you get a very interesting shape for y squared because you reflect that. I don't know how to describe that shape. It's I don't know. What would you... Nah, I'm lost. I don't know what to call that shape. Okay. So that's the sort of idea. So now we go to our one. Now it's a random graph, so I don't actually know the power. So I have to guess. And they look like they're linear functions because they're single roots, they're just cutting through like a single root. So I'm just going to imagine those roots are to the power of 1. And if I find the square root, that makes it a power of a half. Well, if it's a power of a half, then it's going to be concave down. I know it's going to be concave down and a vertical tangent. But it definitely will go through those 3 points. Well, it won't go through, it'll stop because it can't go negative. What does it look like? Yeah, a little bit dodgy on my curve there. I might have exaggerated the vertical tangent a bit here. But I was trying to get that, oh, that's a vertical tangent. I think I might have drawn it a bit too straight. But you get a sort of a rounding thing, a bit like it's not a semicircle, but you know how like a semicircle comes in like that. It's that sort of thing where you get a vertical tangent on each side. This one over here, remember the idea of it's less than 1, so it goes above the original curve, greater than 1, it goes below the original curve. Same with these, I'm going above the original curve, then below the original curve, and so on, and so on. So that's y equals the square root of function x. And if we were to do y squared equals function x, then I would reflect it over. That would be y squared equals function x. Okay, let's have some fun with 5e.